This is the final topic inside our data and statistics section. In this one here, we're going to have a look at a couple of different ways we can look at the relationship between values to understand that relationship in terms of how it varies or if it is significant. In terms of doing this here, we're going to look at two different aspects, and it's really just going to be rounding out or statistical analysis. We're going to have a look first of all at correlation, and then after that we're going to have a look at a non-parametric test, and we'll say what non-parametric tests are. The ChiSquare test is the one we will be exploring. In terms of correlation here, I suppose what we're interested in is considering when we see changes in one variable, what do we observe then with regard to changes in another variable, to try to work out if observed changes in one result in observed changes in another. So it's very useful then just to be able to identify where we see that type of movements across different variables. The important bit on the screen here is actually really quite important, and that's the adage that correlation does not imply causation. So we need to be really careful that whilst we may have two variables and we observe that if we have positive changes in one variable, we also observe positive changes in another variable, that does not mean that that variable is causing those changes in the other or vice versa. So we always need to be careful here where we identify correlation between different parameters or different variables to then think carefully about that underpinning reasons why that correlation may have happened. What was the causation associated with it? So let's start off first of all having a look at correlation. We'll look at what's known as the Pearson correlation, the most commonly encountered one first of all. And it gives us quite a nice way of measuring correlation. It'll give us a value between -1 all the way up to 1, so it's a bounded value. And if we get a value of 1, it's positive correlation between them. So it means then that where we see a certain amount of change in one variable, we will see a predictable amount of change then in another variable based on that. A value of 0 means that these values are not correlated based on the data that we're seeing there, that changes in one doesn't seem to have any impact or bearing on changes in another. And a value of -1 is perfect negative correlation. So in that sense then, when we see 1 increases, we can have a predictable, measurable decrease then in the other variable. How's it calculated? It's really calculated through a measure of covariance. We can see this in the top line of the equation here. Covariance just simply tells you how these two variables differ relative to one another. And what we have in this line is a summation, so we're doing this over all of the data. And we're taking each value, subtracting it from its respective mean, and we're multiplying that difference from the mean with the other observation and its difference from its corresponding mean. And if we think about this then, if two things are correlated, so whenever one thing increases, the other thing increases, then that means whenever our x observation is greater than the mean, our y observation will be greater than its mean, and we multiply together two positive numbers, we'll have a positive number. If it was negatively correlated, then if we subtracted it got it from the mean, it's a negative value, and the other one was negative as well. Again, these things can multiply out. So it gives us a way of actually tracking for large positive values is where we see changes in the same direction. If one value went up and the other value went down, it'll give us a negative value, and if we see it consistently, then it's a negative correlation. And if in most of the cases is up and down, is left and right, and all sort of averages out, then we'll end up with a value around 0. So this measure of covariance that we see here is quite a good one. Large positive values will be related to a positive correlation. Smallish sort of net values means sort of relatively little correlation, and large negative values means there is a negative correlation that's observed. The bit in the bottom line really just is a normalizing factor. It takes both of it basically looks at the variation we see in each of the the different distributions. And by dividing by that, what we do is we take that number in the top line and we normalize it so it falls within the -1 through to 1 range. That's all as it does, just normalizes the variable. So it's really quite a straightforward thing to measure. Importantly, it only measures linear correlation. So there we're looking where we see positive changes in one resulting in a positive negative corresponding correlation in the other, and if plotted, that would be a linear relationship. That's not the only type of correlation you can have. There's lots of different ways you may have a relationship where you observe a certain type of correlation for small values and a different type of correlation than for larger values, so it may be non-linear. But in this case, we're only interested in this as a linear straight line measure of correlation. If we're using Excel, quite an easy way of visualizing this is to draw a scatter plot showing the two different sets, the X and Y with the points, and then simply putting on a trend line. You can pick a linear trend line, and it effectively will show you then a line that draws them through them, and you can look at that and get an idea as to the amount of correlation that you see. In terms of calculating it then as a value, well, of course we can use Excel for doing that. There is the Corel function inside. You pass in two particular arrays and it will give you out the correlation value. So we have some data over here, just an example. We have the number of errors that we observed. You can see the values down here, and then we assume we've asked the user how satisfied they were with the particular task or product, and we see the values down there. And if we put this data into Excel and run through the correlation function, we'll get a value out of -0.78. So that would be an indication that for this particular group of data here, we're observing strong negative correlation. That whenever we have a increase in the number of errors, that generally is associated with a decrease in the user satisfaction. And for the charts, the graphs you can see down the side, you get an idea as to what these different relationships look like. So over here we have an R value of 0.7, so you can see roughly increases in one correspond to increases in another. If it's an R value of 0, so in that sense doesn't look to be any relationship between increases in one and decreases or increases in the other. Moving on now to non-parametric tests. Now it's a slightly unfortunate term, certainly from a programming's point of view, because if we're familiar with dealing with parameters and things like that, that's not what we're talking about here. A non-parametric test is one that doesn't make any assumptions about the underpinning distribution. It's also known as a distribution-free test. And we spend a little bit of time just talking about what that is and why it's important, and then we'll talk about the one test we will have a look at here, the ChiSquared, as our example of a non-parametric test. Now, you might quite legitimately be wondering or thinking about, for things like the t-test or ANOVA or other things like that, how is it possible that we can take a small sample of data and predict how representative that is of that much larger population? How does that work? Well, they're all examples of parametric tests. They do make assumptions about the underpinning distribution. And those assumptions actually are fundamental to the predictive model that's built into these different types of tests. So most often they assume that it is normally distributed, that your big population is normally distributed. There will be one typical mean average value, and you'll have sort of a normal distribution around that. Most values around the mean and progressively fewer out at the extremes. And if you make that assumption then that that's what your overall population looks like, that's the truth of your population, you can then reason about, if you were to take a sample at random inside that, what is the probability that it is a reflective sample of that overall distribution. Now that's important because in a lot of the things that we've been talking about through the parametric tests or t-tests and so on, they only really work if we do have a normal distribution. If you were dealing with data that did not have a normal distribution, that was bimodal, for example, the users either love it or hate it, there's no average value, there's two distinct peaks, then we can't use some of these tests, or if we do use them, they're not going to be as accurate as they purport to be, because our modeling assumption about the underpinning distribution is different. Non-parametric tests we can use. They're ones where we make the assumption we don't know anything about the underpinning distribution. Now, in making that assumption, we're almost accepting then, but we're going to have to be more cautious about the conclusions that we can make, because we don't really have any underpinning assumptions we can build this upon. But if we have things like nominal or ordinal data, then that's the type of test that we need to use, because we can't use t-tests or other ones because it's not meaningful to talk about the gap between individual data values. And for example, we will commonly encounter this. So if we're dealing with data where we're asking about differences between males and females, or beginners, experts, and intermediate users, they will require a non-parametric test. There's lots of different types. We'll have a look at the ChiSquare test, which is probably the most commonly encountered and used test. The ChiSquare test then, it's a similar pattern to the other ones that we've seen. We're going to calculate a ChiSquare value, and that value is going to make sort of good logical sense in terms of what it measures. And we're then going to compare that to a critical value. And that's going to be a value we'll look up or get from an online calculator. And in terms of looking that up or calculating that value, we'll pass into this our confidence level. So it'll give us a value back that will depend upon the level of confidence that we want. And will also depend upon the number of degrees of freedom, but we'll talk about that in a little bit. We'll compare then the two values. We'll compare our calculated chi-squared value against our critical value, and depending on if it's greater than or less than, we'll be able to conclude if the data that we've seen, if it is meaningfully different at our level of confidence, or if we can't make that conclusion at all, and potentially it's from the same sort of overall distribution, again at our level of confidence. So let's have a look then at the chi-squared value itself. It's quite a simple calculation. So you can see it over here on this particular side. We're looking at an observed value, and we're taking away from that the expected value. And we'll show you an example on the next slide that sort of typifies that for usability tests. So that gives us the difference between the observed and the expected, and we square that. So it's going to be positive, and the bigger the difference, the more significant it is. And we divide this then by the expected value. So it gives us a way of normalizing this. We add all of these things up. So it gives us then sort of then a total value measured across all of those different aspects. Now, having done that then, we want to calculate our critical value. And as we said, that's going to be a lookup value. We'll pass in either our confidence level is 95%, or the alpha level is 0.05 in terms of an error rate that we're prepared to do. The other parameter then is one that ties into the number of degrees of freedom, basically the number of variables or things that could change or differ inside the observed data. In most cases, if we're simply dealing with just tabular data that we're passing into this, it's based on the number of rows by the number of columns. Crudely gives you our number of degrees of freedom. So you can see an example of it here. We're using it, the ChiSquare.test is built into Excel. It takes in two parameters, the actual range and the expected range. So again, this can be in terms of what we observe and what we expect. And normally, just give you an example over here, and this is normally the pattern we would use then for usability tests. So over here, we assume we've got some measure of task success. We're asking users to do a task, and they may be able to do it or they may fail to do it. And we've segmented our users into experts, intermediates, and beginners. So here we're dealing with a class of data where it's not meaningful to talk about the difference, but the delta between an expert and intermediate and a beginner. So we have to use a non-parametric test. In one sense, let's say for our experts, we did 16 tests, and 15 of them were passed by people we've classified as expert. Whereas, for example, for beginners, we've done 15 tests, and 7 of them were passed by users we classified as being beginner. And if we wanted to ask the question, based on the data that we have seen here, can we confidently, say with 95% confidence, say that these results are meaningful? There are meaningful differences between experts, intermediates, and beginners at a 95% level of confidence, or can't we say that? Do we not know if that's the case? Passing it into the ChiSquare.test inside Excel and running that, it'll give us back then a value of 0.04 over here. So if we were working at 95% level of confidence, so that's a 0.05 error rate then, in this case we can say for the data that we have observed here, we can be 95% confident that there is a meaningful difference between how experts, intermediates and beginners, the number of errors that they make when encountering that particular task, or their ability to pass the task rather. We couldn't say we're 99% confident because our ChiSquare test value, the p-value, is greater than 0.01. So that gives us a bit of an indication as to where we can define that. And that's all we want to cover inside our look at data and stats. We've looked at sort of a wide range of different tools. Hopefully all of them are sort of understandable. They're quite easy to use, certainly by using the functions available inside Excel. What we're going to look at now are actually some actual tests that we can do, or ways of self-reported metric that we can get back from the user. And doing this here, it'll give us data then that we would then use the various types of statistical analysis to analyze that data. We'll put in interval bars, we will talk about the confidence we have in it, we will compare one data set to another. So all of the statistical tools are how we will analyze the data that we'll now get from the usability test that we're going to go on to have a bit of a look at.